Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Let's just get started, please, with our first speaker, Germ and Molt from the University of Valencia, please.
Management and contextualization of scientific virtual appliances. And here is the outline of the talk. I will start with a brief introduction and overview to our research group, and then I'm going to focus specifically on scientific cloud computing. In particular, I'm going to talk about contextualizing virtual machines and how to manage them using repositories and catalogs. Finally, I will talk about scientific applications in which we are applying this kind of techniques. And finally, I will end my talk with some conclusions and future challenges. Okay, so our research group focuses on applying different computational techniques, such as parallel, distributed, grid, and cloud computing technologies, into different scientific fields, such as engineering simulation, photonics, proteomics, biomedical computation. We typically establish collaborations with research groups so that we can apply this kind of techniques. And if we have learned something through all these years, is that scientific applications typically require large computational power and also processing large amount of data. So this is why typically combine several techniques, for example, high-performance computing and grid computing in order to solve large dimension problems. And specifically talking about grid computing, this has been a technique that has been successfully employed in many areas. And perhaps one of the most important approach of grid computing is that it has leveraged scientific collaboration in the shape of virtual organizations, and it has allowed to access a large pool of computing power. But it has also some drawbacks. And if I had to mention just one, is that using grid computing, the main problem is that it is resource providers, the ones that define the execution environments. And this is one of the key areas that virtualization and cloud computing tries to solve. Because with cloud computing, it is resource consumers, not resource providers, the ones that define the execution environments in the shape of virtual machines. And having a control environment is especially important for scientific applications. But cloud computing has also another advantages, and is that it allows dynamic scaling of infrastructures for resource providers. You as a user can have a fast and easy access to a large amount of resources. And virtualization, which leads to server consolidation, also leads to reduced energy consumption. Now, if we focus on the point of view of the scientists and engineers, they don't want to bother with technology. They just want to run their applications as fast as possible and to solve large dimension problems. And when we talk about grid technologies, we have lots of concepts and tools that complicate life to users and developers. And now that we are talking about cloud computing, we also have additional problems, which hypervisor I'm going to use. I'm going to configure, deploy, and monitor my application, which IPAs I'm going to use to program. So I think it's time to focus on abstracting the details of application porting to the cloud. And in particular, in this talk, I'm going to focus on the lowest level of this typical classification of cloud systems, where on the top level we have software as a service and the user application. On the middle, we have platform as a service, where application developers are provided with APIs to develop cloud applications. On the lowest level, we have virtual machine managers, which provide the enactment of management on virtual machines. And we can currently find lots of virtual machine managers currently in the literature. But we are currently considering these key factors in order to decide which one we want to focus on. And we want them to be open source. We want them to have access to public clouds, such as Amazon EC2, have wide variety of APIs, very important for designing applications, different hypervisor technology supported, contextualization support, network management, and also ecosystem, a wide variety of users, large community. And having these key factors in mind, we're focusing on Open Nebula, Eucalyptus, and also we currently keep an eye on what the Nimbus project is doing. Well, virtual machine managers focus on supporting the life cycle of virtual machines, but for scientific cloud computing, we also require automatic contextualization of virtual machines in order to get scientific virtual appliance. So, and also we need to reuse different virtual machines among different experiments and also between different researchers. So this is why we focus on application contextualization and also their management using repositories and catalogs. Okay, virtual appliance is very well-known term. It's just an encapsulation of an application requirements, and operating system. It's just like a minimum execution unit in a cloud. So, but if we're talking about scientific virtual appliances, then things get a little bit more complicated, because these kind of applications might require a certain operating system, certain services from the operating system, for example, transfer services, persistence layer, either database or files, simple files. Special middlewares, for example, grid applications might require the Globus toolkit, for example. Computational libraries, you might have a scientific application that requires numerical kernel, such as BLAST or LAPACK. And finally, you have the application and the application data. So creating scientific virtual appliance is not a trivial task. So going from a virtual machine where you have the plain OS into a scientific virtual appliance where you have finally the scientific application running, this typically requires a process called contextualization. And contextualization means creating the appropriate hardware and software environment for a successful execution of an application. And this typically happens at two levels. Because first of all, virtual machines have to be contextualized. When the virtual machine boots, for example, it needs outbound connectivity. And this contextualization process, its support is provided typically by the virtual machine managers. But then you have to contextualize your application so that it finds the appropriate environment. So that the applications need to be deployed, configured, built, and executed. And we can currently find lots of tools out there for machine configuration, which allows dealing with automatic machine configuration, and also the installation of commonly used packages, very comprehensive tools. Many of them are in the shape of client service tools, but we wanted to focus on the specific workflow for deploying scientific applications. And things typically go like this. First of all, you have to resolve dependencies. Applications might require on other related packages or system packages, so the dependencies have to be installed first. Then you have to configure applications, which means a subset of actions, copying files, changing properties, declaring environment variables. Then you have to build the application using different build systems. And you finally have to start the application, which depending on the application might require invoking a script, starting an application, parallel execution, or whatever. So we're currently working on software for application contextualization. And the idea is to inoculate software and configuration into the virtual machine without with minimum user intervention. So we currently have this approach. We have the user that has the application, and the user or the developer writes the application deployment description in XML, high-level language, no programming skills needed. And together with the software dependencies, this goes to the contextualizer tool, which creates a contextualization plan so that in the virtual machine, packages are installed, configured, built, and the application is run, so that we can perform the deployment of the application at boot time in the virtual machine. So we currently have a proof of concept tool of this application called it in Python to ensure good portability. We have a plugin-based mechanism so that users can write just XML deployment descriptions, no need of programming skills. And we currently stage the tool, the application and the application requirements into the virtual machine at boot time, creating a special disk image, so that when the virtual machine boots, it can start the contextualization process so that we can go from a virtual machine to a virtual appliance ready to execute the application. Now, cataloging is also an important feature that we want in order to reduce or enhance collaboration and virtual machine sharing. And it is true that there exist VM catalogs out there, but they focus specifically on human consumption. They don't provide APIs, work on unstructured metadata. And we wanted to work on a catalog that includes virtual machine metadata, a description of the operating system and the software environment, very important to execute applications. And we use the open virtualization format, which is XML-based, to describe the features of the virtual machine. We also want to provide links to other repositories, which are either local or remote. And we're currently working on matchmaking algorithms to retrieve the most appropriate virtual machines according to application requirements. This is one area in which we are working right now. So we currently have this approach. We have the user, which provides the OVF description of the application, and it talks to the catalog to register the virtual machine. And the catalog creates an instance of a transfer manager, which creates temporary credentials, which are delegated to the user in order to upload the disk image size to the repository. And this image size is registered in the catalog and conveniently tagged so that it can later be accessed. Now, concerning the repository, it includes the storage of VMs and provides data access mechanisms. We currently include HTTP and FTP, very well-known protocols, but we're also considering including grid FTP, which would provide an enhanced certificate-based security. It's a protocol for transferred files. And the current virtual machines that we are considering is golden or base virtual machines, currently based on Ubuntu Juice, which provides a full operating system in just 380 megabytes. It's very important, very low footprint. And also having pre-contextualized virtual machines. For example, for grid applications, we have virtual machines where we have already the Globus toolkit for deployed, so that we can contextualize just the grid services that need to be deployed. Well, so this is the big picture that we currently have. We have the user with the application requirements, and these application requirements are submitted to this Cloud Enactor component. This Cloud Enactor component talks to the VM catalog in order to retrieve the most appropriate virtual machines, which are retrieved from the repository. And then it talks to the contextualization software, which must compute the deviation from the virtual machine and the application requirements, so that it must create this contextualization plan, which is submitted to the virtual machine manager. And the virtual machine manager starts the virtual machine. And when the virtual machine boots, it starts the contextualization process, so that you finally have your scientific application running on this virtual infrastructure. Well, there's a missing point here in this figure. And the point is how I'm going to control the application and access the output files inside the virtual appliance. And we're currently relying on the Opal2 toolkit, which is a tool developed in NVCR. And it provides a web service wrapper for applications. And it was initially developed to provide a wrapper to legacy applications. But it is very, very useful in this kind of environments, because it allows operations for remote starting, monitoring, and terminating the application. And very important is that it also allows to access the output files while the files are being produced, because they are exposed as a Tomcat service. And this enables to introduce computational steering. I mean, to see how your simulations or your executions are being processed and the output data are being written in files. This is a very important approach. So once we have these web service applications, we have the hardware hypervisor and then the virtual appliance, which runs the scientific application and a web service wrapper that allows this Cloud Enactor component to control these applications, to start, to monitor them, and to access the output files. This is currently the approach that we have. Now, what kind of applications are we using in this kind of techniques? We're currently considering 3 different applications: simulation of cardiac electrical activity, simulation of guided light in photonic crystal fibers, and also optimization of protein design with target properties. These are applications that we have been working in them with collaboration with other research groups in the last 5 years. And there are applications in which we have previously applied high-performance computing and grid computing, and we are currently investigating how these applications can benefit from these cloud infrastructures. Okay, so just to wrap up, I would like to add some conclusions. Scientific cloud computing requires tools to abstract the interaction with cloud infrastructure. So going from applications to scientific virtual appliances is a key point. We are working at application contextualization and virtual appliances management. And we think that the cloud looks an alternative approach for executing scientific applications. And the main benefit over grid infrastructure is that it allows to define the specific execution environments. This is one of the crucial points. We also see some challenges in the near future. One of the most important is that, for example, if infrastructure providers currently are different silos, so probably software gateways should be developed to aggregate these kind of infrastructures. And we also see a large ecosystem of virtual machine managers. Many of them share the same functionalities and goals, so we will probably see in the near future the rise and fall of some of them. And it is true that there exist common APIs for cloud computing, so that you can develop your application against one single API, and then you can access different cloud infrastructure. But we'll have to wait to see how these projects evolve in time. And a final thought is that clouds and grids will provide computational support to scientific application. Okay, and this is what I wanted to tell you. So if you have any questions, I will be glad to ask you. Thank you very much.
Dr. Bill.
Okay.
Yeah, the room's
It's
mic.
for the recording, but it's not because of me.
I think the room is mic.
So you mentioned this concept of pre-contextualized VMs. That would, in my mind, before I started your talk, that was sort of the only kind of virtual clients that I really think of as things where people sort of, developer will install the software they need for a particular application, get it running, and then save it off as a virtual appliance, and now anybody can run it. So the automation step that you're offering, where someone expresses at a high level application requirements, then automatically just create a VM. I guess I'm not quite clear why that automation needs to exist. I mean, at some point somebody has to manually kind of construct the application stack once, at least somewhere, to prove that it works.
I agree with you. The first time you have to manually configure the virtual machine in order to install the application, but you can replace this manual installation process with an automated process. And this automated process is...
Once at least, right?
Yes, this is true. This is true. But this is true if you just want a single infrastructure. For example, if you are using Amazon EC2, you just create a specific virtual machine for this infrastructure. But imagine that you might access different infrastructures simultaneously. And for example, Amazon EC2 uses Shen hypervisor. Then you can use other infrastructure that uses KVM hypervisor. So you might find it in a situation where you have to deploy the...
Every possible vendor, and that's what it's got.
But I agree with you that once you have configured the application, you can save it as a pre-contextualized virtual machine so that you can later be reused.
Any other questions?
Maybe I have one more.
Okay.
You mentioned in the sort of data flow diagram you showed, at the first step, the user expresses application requirements. How are they expressed?
Currently, we're working with OBF, but we think that OBF is quite much. It is XML document, but it is lots of expressive. I mean, we're currently thinking about a transition to another, probably most appropriate format without being too much expressive, because many times the applications, the requirements of applications don't need to be so much expressive. So we currently have a proof of concept using OBF, but we will probably transition to another approach.
Hi and welcome. Well, I see that my presentation is very different for all the previous ones, as I'm going to present you our project that was, application was built to demonstrate a proof of concept and technology and to use our tools that were available to us. I come from University of Maribor in Slovenia, and I'm part of Cloud Computer Center there that was established in cooperation with leading business partners in our field, such as Microsoft, IBM, and Oracle. And the aim of this Cloud Computing Center, which is actually the first in our country and also the first in our region, is to transfer technology and knowledge between academic sphere and business. And besides researching and preparing our PhDs, me and my colleagues also assist at pre-graduate student programs, and we try to motivate students additionally by including the newest concepts of the computer science into our classes. So as a practical part of one of our courses, we've decided to give students an assignment to write down a few ideas about practical use of cloud computing. And then we've collected those ideas and selected a few of the best ones. We built a high-level architecture and divided students into several groups. Each group then built partial solution individually, and at the end of the semester we integrated these solutions into final applications. And this project called SKYINFO was one of those applications, and it showed enough potential that we decided to carry on developing it even after the end of the course. The problem that this project is referring to is, I'm sure, well known to everybody. In today's information society, every individual is overwhelmed with large amount of data that is surrounding us, and most of this data is unimportant, and it only makes it harder for us to get to the information we really want. And also a lot of time is wasted processing this unnecessary data, and during this time a lot of information that we're looking for can already become obsolete. Well, to overcome these problems, we've decided to filter all available data in relation to individuals' current location and expressed interest. Therefore, SKYINFO is designed to offer an intelligent, anytime, anywhere available service, which will provide users with relevant, localized, and personalized information. The main idea is that on the first side, users submit messages about events they witnessed, either by writing a text message or by submitting a picture. And on the other side, they receive events from other users based on their current position and subscriptions. Each subscription defines a category of a message to be retrieved, and also maximum distance and time validity of a message. Of course, considering this solution, we've also encountered a few problems. The first problem was that multiple people can witness the same event and send a message, so we had to develop an algorithm to identify those duplicates and treat them properly. Another problem is that after user sends a few false messages, his integrity should certainly be questioned. Therefore, we designed a rating system that works on feedback. So every user who receives a certain message can respond to it, and either confirming it or denying it. And either confirming it or denying it, and based on this feedback, message and user's rating is updated. We have considered a lot of use cases for our application. These include reporting of traffic accidents, reporting of traffic jams, and other traffic information, warning about approaching weather conditions, reporting lost and found objects. Another interesting idea is localized advertising, and so on. Here we will take a closer look at one of scenarios. Imagine Mary, who is walking in a park on a sunny afternoon, and she finds a sad puppy who obviously got lost. She takes a picture and submits it to our system, and luckily the puppy's owner is already looking for the puppy nearby, and he also uses our system, and he instantly receives a message with position, and thanks to our system, quickly puppy and his master are joined together and happy once again. Here we have a presentation of this high-level architecture. We've decomposed the application into several modules. With this, we've enabled loose coupling of components, and later I will mention that we've decided to implement each of these components using web service technology. The main part of SKYINFO application is distributing messages. Therefore, we've tried to develop an innovative approach to exchanging data about occurred events. So besides considering location and time frame, we've also tried to simplify the process of submitting messages. To submit a message, user only has to fill out a description and select a category, and then a system or client, for that matter, automatically gathers location either from internal or external GPS or from other available methods. And then these messages are distributed back to clients which continuously report their location to our system and retrieve new messages. There's also another way for urgent delivery of messages. At the request of the user, messages can be delivered directly and instantly over short messaging service. The way of sending messages, text messages, which I just presented, seems to me to be as simple as it could possibly be. But we've gone even further, and we've developed another innovative approach of exchanging data about events. Here, users can only submit a picture, a plain picture that can be submitted either over call to web service or through email or multimedia messaging. And thanks to use of Amazon's Mechanical Turk service, we can classify this picture into one of available categories. And of course, system, I forgot to mention, the picture has to include geolocation. So this means many devices nowadays already support that, so this is not a problem. Here I have an example of a human task that is built by our system. Mechanical Turk provides a programming interface for building human tasks which are available online, and any user on the web can work on them. So I think it's a very interesting alternative to computing methods and algorithms which are, at least for image recognition, very complex. Well, our project is still a work in progress, but so far we've built a first version of core system and two clients. On this picture is a mobile client. The first one is built in Android platform, and we have intention to build another one for Windows Mobile. We had some problems calling web services from version 6.5, so we decided to wait for version 7. Here is, on the left is a presentation of new messages. On the right is the form for submitting new messages. This is a web application which, besides displaying messages, enables user to subscribe to categories. It's built in Microsoft Silverlight technology. Another challenge that we faced building this project was integrating many technologies. For this purpose, we've employed web services. So those gave us kind of a bridge between different platforms. The core services of SKYINFO are built in Java and running on IBM WebSphere application server. The supporting services are built in Microsoft.NET and are running on IIS server. And we've moved first of our services already to Windows Azure. And the ones that are built in .NET could easily be transferred, all of them, there as well. For human tasks, as I already mentioned, we used Amazon Mechanical Turk. And for web interface, we've used Microsoft Silverlight. Then for mobile clients, we've used Android and Windows Mobile. And of course, a big part of our service is using maps. We've used Bing and Google Maps. Well, the key contributions of our project, I believe that linking relevant information and events with location and user interest leads to quickest access to desired information. And I think that our approach to exchanging data about occurred events but submitting only pictures is very innovative. So to wrap up, I would like to say again what our project is all about. Well, it's basically a framework for sharing information in a structured and personalized manner. Therefore, we would like it to be useful for general public. SKYINFO could also be distributed as software as a service. We believe to the organizations that require private information service. That's it.
Questions for a speaker?
I have one. So you use Mechanical Turk for that, some of the image classification in the cloud, right? But you also have the users when they submit events into your cloud-based app. They classify them as well, right?
Yeah, there are two different ways. You can submit a message. There you have to select a category, but if you submit only a picture, the picture is classified using Mechanical Turk.
Okay. And how is your turnaround time on Mechanical Turk classification?
Yeah, we didn't test that in reality. We only tested in the sandbox till now. So we did the human tasks ourselves. It was quick.
I have a question. I live in a city near São Paulo in Brazil, and São Paulo gets really terrible traffic jams.
Yeah.
And I would like to present you a scenario and see how SKYINFO would respond to that. For instance, you have a traffic jam, and hundreds of users start using their cell phone, sending pictures with the cars in front of them stopped. And these images are geotagged. But I'm there on Snoopy Avenue sending pictures, and am I on northbound or southbound side? Can you decide that based on the geotag? And if you're receiving hundreds of images of cars stopped, could you infer the reason of the traffic jam, or would then be useful if only a few cars would be close enough to the reason of why the traffic stops?
It's an interesting point. I'm sure that it would be useful to know that there is an accident. I don't, with our, what we've done so far, it's impossible to tell on which side of the road is happening, but you get some basic information. Maybe users can write it in description. That's another way.
Good point. I realized that you didn't mention what do you do with the content of the SMS text message you receive. Do you also use human users to process the content?
No, we just distribute it to the users that are receiving messages. We made some algorithms for identifying duplicate messages. These do read the content or try to find some patterns.
So some questions. How do you distinguish your system from a pub subsystem in the cloud, where people can actually subscribe? You know, have interest in certain events, and you're just simply routing those messages in the pub subsystem. What differentiates your system from it?
I didn't understand.
So you're actually generating these messages from the devices out in the field. You're routing them up to the cloud. You're looking for subscribers or people who are interested in them and routing them to them. So my question is, and that's a very similar pattern to pub subsystems, publish, subscribe. where people subscribe to events, other people are publishing events. I'm curious if you're taking a different approach, if your platform is different from a pub subsystem in terms of your processing or the scalability, or have you compared it against pub subsystems?
No, I'm not familiar with it.
Okay, that might be something interesting to look at. Have you done any scalability in terms of how it scales in terms of event loads? And
well, we actually are running this in a private cloud, but we haven't done extensive testing.
Any additional questions? Let's thank our speaker.
Thanks to everyone. What I want to present is also for me, for us, is a proof of concept. I am a computer science engineering working for a chemical engineering laboratory that is called MOSE, that does technology that will revolutionize the world of research, that is called multiscale molecular modeling. This technical approach is applied in three main fields, that is material science, life science, and process simulation. What is multiscale molecular modeling? The multiscale molecular modeling is an approach that allows at the end to simulate a process at engineering level beginning from a quantum mechanics level of simulation. But this is a multiscale because there is no computation processing resources available now and in the near to medium to far future to simulate this on real time. So multiscale means that we have many stages that you can buy at single, but the main is to simulate the process from quantum mechanics level, arriving to the engineering level. How do we solve the problem having many steps to resolve this modeling? It's a message passing multiscale. So we have, in general, we have many software that simulate the same process or the same process remodeled at the proper level. Each result, each input, each application have an input, it simulates the process, and then the output is passed on the next level. This is mainly a sequential process, but this sequence of activities can obviously be modeled in a cloud. So the sequence of activities can be distributed worldwide because the laboratory collaborates with many other figures, laboratories, companies. So the laboratory is able to simulate inside, but can also distribute the work around the world. At the same, the customers are worldwide. But at this moment, the laboratory is not on the cloud because we are based on software that is not on the cloud. The simulation software are not on the cloud. So we made in-house. We have a pile of servers on which we made some simulation. But specifically, this proof of concept is also useful for us to talk with these people that give us software, or internally how we can do working computation on the cloud. Also because we need the cloud, because cloud is a useful collaboration platform, so it can allow us to distribute the work around the world. Can Mose access along the cloud alone in terms of his focus? So chemical engineering, so with chemical engineers that are the typical users. You have to understand that I am the only computer engineer inside the laboratory. So often they need also to write some code. The simulation, but also some code that can parameterize some of this software. The idea is to help these people writing some code that can execute on the cloud. So the objectives of this research is to move the laboratory on the cloud. So we cannot wait the software company to do this, so we try to do something to make this work. As I told you before, we as computer engineers, we can write this, but there is always a big problem that is the domain problem. What does a molecular means? What does an engineering process mean for a computer science engineer? So the idea is, why don't we enable non-computer scientists writing their own code, simplifying writing their own code? One aspect we have to understand that at this moment, one thing is what non-computer science engineer can do, what tools at the moment, for example, simulation software ask to these people. And it's normal today to have that this kind of software are accessible only in C++ code. That is quite difficult. So, for example, one activity we have done with another group is moving the code to the CLR code, writing in C# or VB.NET instead of VB6 or worst in C++. The next step are the usage of dynamic languages like Python or Ruby, and then also the usage of domain-specific languages, DSLs, that can abstract on another level the way we can express code and data. Just a few slides. I'm not Microsoft, but I like to share with you technologies that are from Microsoft. They are from since, for example, IronPython is about 3-4 years, but is not so everywhere. There are a lot of few people. Dynamic languages are on .NET, and someone that comes from the open source community is now part of Microsoft, is called Jim Hugoning, and has developed the first version of IronPython. And the nice thing of the work is that IronPython was split in with version 2 in two parts. One is that is a specific part that is the IronPython language. The other thing is the dynamic language runtime. That is the common part for the dynamic languages. In fact, we are waiting in these days probably the version 1.0 of Iron Ruby. That is the other main language in the dynamic community. One of the big things is that these languages run natively in .NET, so they are completely CLR types, so completely managed code. They run under Azure, as we will see in a few minutes. They are quite advanced. For example, IronPython is already Unicode code, and there is some problems with original Python code that is not yet Unicode. And the nice thing is that dynamic language runtime allow other code. For example, JavaScript that is coming from community. We are having a native JavaScript language running over runtime. And if you don't know, the DLR is also under C# 4.0 and on .NET 4.0. That is, in 4 days we will have the final version, because the dynamic keyword in C# is in effect a part of the DLR. In fact, Jim has moved to the C# team. This is one technology that we are using to allow non-computer people to simplify their programming abilities. Another tool that we are starting using is Oslo. Oslo, that is already named as SQL Server Modeling, because this, we can say, a research project, but that was not a research project, is becoming a product that will be out in a long time, because it's 2 years. What is Oslo? Oslo is a part of a data platform from Microsoft. Has this component, M-language, the quadrant tool, and the repository. What is Oslo? Oslo is a framework of tools that allows us to create dynamic domain-specific languages. So we can write code. We have a tool on which we create in a simple way languages, mainly textual languages, while Quadrant is a visual tool to interop with this with domain language. And this is useful also because if we use storage under Windows Azure, specifically not SQL Azure, but Azure storage, blob, tables, or queues, but mainly, for example, blobs. Oslo, what is Oslo? Oslo is a tool that allows us to make a parser for unstructured data. In fact, yesterday when Ed Lazowska told that scientific world lives in a big amount of unstructured data. Well, Oslo is a nice tool to structure the data. In particular, Oslo is a schema language to give a schema to any data we want. In fact, this is the way. This is why Oslo is get into SQL Server. It was SQL Server platform, or mainly the data platform. So, which are the simplification steps? What is our proof of concept? We have written a Windows Azure application, specifically a web application, a web role in an Azure application with MVC2, and a worker role for background processing. What we do with this web application? We load Python scripts, for example, that are executed in a worker role. How do we interact with this dynamic language, with this jobs that run on a worker role? We do input and output with textual messages that are parsed with Oslo. So we see a demo to fix the correct messages. I have some just to see what Oslo is. A file that does not relate to the example, but to see what are unstructured data. I have downloaded a comma-separated file from a business website on which you have money changed. This tool is called IntelliPad. In the center, you have a grammar that is an evolution of a typical Backus-Naur form grammar. This tool has the nice thing that you write the grammar. On the left, you have the source. And on the right, you see you have the M graph that is, in this case, is the serialization of the abstract syntax tree that is generated from this tool. So this is to show you that how to structure the unstructured data. Specifically for this example, okay, my example is quite simple, is a matrix multiplication. But suppose you have an input made in this way, not in a coding way, a way that is probably similar to MATLAB, for example. Okay, you have two variables, E and M, a vector and a matrix. You see that there is a grammar, and then you have the result of a parsing that is accessible to a programming language to load the data. This is the input. The output I find, okay, the output, which is the part, the output, is a template in which the results are written on a text file. So in this way, with Oslo, I have written a grammar in which I parse a template. And you see text, expand, text, expand. If you write this, you make for each, write, read the text is just write the text. Expand is read the value, write the value. Okay? With Oslo, it's quite simple to write these kind of things. So if we see the application, I have done a simple application. Quite, I would like to call it the Facebook of code, but probably it's okay. Here we have, for example, as a publisher, I can write some Python code, and you see what can be simple. You don't have an environment, you don't have Visual Studio, you have just a web page on which you write the code. Just the code you need. Okay, simple matrix multiplication in Python language. And sorry that the zoom is not good. But for example, here you see dictionary of math, that is the schema, that is the parsing of the input. I need a dictionary, and I have an output that is a M per view report. That is the template we have seen, that are defined in an administrator part. I have the math of dictionary and the report. So you see that this web application can organize the code, the project, for a person that has no skill, for example, with Visual Studio. How you can interact with this application, you have to send the messages. So, for example, you have a request on which you define, I want a batch processing for this component. Then I give the input, simple. Okay, simple message, matrix multiplication that makes the multiplication of the double of the square, sorry, of the values. Save. So in this moment, when I have saved on table, I have already sent a message on a queue that is written on the queue. So this trigger the worker role that read the message, find in which language is written the code, and then you see on a refresh that is posted a message. It is, okay, I have made a mistake because I need a vertical vector, sorry. So I have to put the comma. The comma. Oh. Okay. This obviously this is a web interface for the people. Think that we replace with this with a WCF web role on which we have a REST application in which all the information are serialized and then parsed. Okay, you see that is 1, 4, 9, 16. That is just the multiplication. This is the demo. So back to the presentation. Just to say that the matrix is too simple for the code. This is the result of one of the simulations we do with our software, but we think that this is just a little more complicated matrix multiplication with a matrix that is quite large. So in this way can be useful, the cloud, because we can divide that information on multiple worker roles, multiple instances of a worker role that can elaborate the multiplication. So the result, the proof of concept is that all these pieces work together. This is working under the, if I have not shown you, but this is the Azure development environment. So this is the code that can be supplied to the real Azure account. The conclusion, why Mose need the cloud? Because we need a platform that allows us to create with this messaging-based application. And in the demo, we have seen the creation and the execution of a simple step in the process and the input and output that are more near to the scientific world than the information world. You have not seen the XML that was quite typical to write parsable texts, but was quite awful to be used from scientific people. The code, we have libraries that define these components, that invokes, for example, IronPython, and invokes Oslo. What's next? The next is obviously continues with the project. One of the ideas is the definition of a project, and I have updated the presentation just to locate our work. The presentation yesterday from Paul Watson, that the person who made the workflow of the components. Well, our work is exactly, this proof of concept is exactly the single workflow step. And now we need also the entire platform. Collaboration in the process, so how do we share these input-output messages? So blogging tool can be useful. A Twitter integrated with a platform can be also useful. Well, the next is the verticalization of a domain. So Python is useful, but we can abstract again. How? Writing a DSL that is a real language. I made here. I cannot do the demo because I have written the code in with November CTP that is .NET 4, while Windows Azure is 3.5, and this is why yesterday I asked when cloud will be 4.0. This is a grammar for a language, a custom language that has the same output, But the idea is to have, yes, we can have a standard tool that allow us to make the normal operation, probably in a more verbose way, to be readable, to be more understandable from scientific people. But it will be interesting, for example, having a mixture of a Python syntax, having LINQ-like syntax to interact with data sources, but avoiding connection strings. And this is nice because living in a cloud in Windows Azure, we can abstract what the need for connection string and say, we are on an Azure account, so give me that particular blob or table or queue object. So this is it. This is, as I told, is a work in progress, and I think it's also an invitation to use these tools because they are very, very useful. Thank you.
Questions for the speaker?
I have one. So is your bottom line goal with all this to make it easy to find specific languages to pass standardized formats around multiple simulation codes offering each size scale? Or is it to rewrite simulation codes into something that runs in the cloud environment?
We can, the first step is the idea that we can allow to abstract as much as we can the programming environment to the chemical engineer. Then, if he can write code, he can try to write the code he needs, so also the simulation code. There are many, for example, one of the examples is the process engineering, in which you have mixer, splitter, reactors, which can be written in some code that can be expressed in just few equations. So what we want is not to make the chemical engineer write a class, a function, but just write the equation, declare which are the inputs, which are the outputs, and then execute it. The Azure, these techniques can be applied outside cloud, obviously. The nice thing of a cloud is the storage, because the chemical engineer, when in front of a computer, does not know where to save information. He only writes text files. So Oslo can define the schema. Azure can save these files in a reliable way because it's quite important.
So once it's defined and saved, how would a group of chemical engineers, which is distributed along several nodes, how could such a group cooperate, combining, reusing these components?
In this demo, you have not seen a collaboration platform. In fact, I have written that we need to define a process.
Okay.
This proof of concept works on expression. So, we can abstract the programming skills to the chemical engineer? So, simplify the work to the chemical engineer. Can a chemical engineer write some code? This is the first answer that this work do. The next step is to make the real platform that allows the collaboration. As I told, the work presented yesterday from Paul Watson showed that other people are working on the same argument.
More questions for the speaker? So I have one for you. So first, I was really surprised to see Oslo. Pleased to see Oslo in action. not seen very many demos of it, so I really like that. But can you talk about the applicability of Azure for running some of the simulations? Because a lot of simulations are tightly coupled. So the kind of simulations you're targeting, are you finding you can actually fit them onto one worker, or can you talk about the class of simulations you're targeting right now?
This work is a ticket for us to go to the simulation software companies to say, well, bring your software on the cloud. So we have in Trieste there is a company that does this kind of work. There is a project on this, and this can be a sort of another runtime. we can say that, or in Python or on a DSL can be another specific runtime that can be the runtime for this application, for this platform, from this software company, to bring their software to the cloud. We know that we cannot write an entire simulation, but it's an invitation to port the code from this company. Have to bring the code to the cloud.
So you're focusing on domain-specific languages for the researchers to use, and
what I see is that the chemical engineer have many difficult to match. So we have to abstract, and Oslo is not a revolution in terms of languages, because we have probably more powerful tools. For example, ANTLR, that is the component that can generate parsers for us. But Oslo is a typical Microsoft tool. Is a very simple tool to use. It's just we can relate to Oslo like we relate to an XML DOM. It's the same, but because you know that the DOM-box work is one of the in fact, yesterday I was yeah, I show you. I have. Oh, sorry. I was with Douglas Purdy and with DOM-box to ask what Oslo will perform, but DOM-box says give a schema for text files, for generic text files. This is the objective.
Just real quick, I just want to re-ask one part of Roger's question, which is there's sort of at least two sizes of simulation, right? Ones that work on a single node and ones that don't work on a single node. And one part of Roger's question was, do you tend to support the ones that do not work on a single node but require sort of orchestration among many, many nodes? And if so, how?
As I told before, we know that we cannot rewrite an entire simulator. No, so
it's not about rewriting. I guess it's just there's a scale problem, I suppose. That even if someone else comes in and writes it and hands you a CFD simulation, a computational fluid dynamics simulation, that necessarily runs in parallel because they're enormous. Azure may not be the best fit for that for some of the reasons Roger mentioned. Do you intend to just ignore which is fine?
No, I understand. No, the idea in this way with DSL is to model to simplify in DSL the way we can express the distribution of a computation. So try to abstract. Our objective is always writing verticalize the domain. So knowing that there is difficulties to divide the process in parallel, the idea of DSL is abstract also the parallel abstraction in the language. So to try, obviously, to make it accessible to skilled and non-skilled programmer.
Let's thank our speaker one last time.
Thank you.
Our final speaker of the session is Domenico Talia from the University of Calabria, talking towards an open service framework for cloud-based knowledge discovery.
Thank you. So my talk is a discussion about the strategy for the implementation of a service-based or service-oriented framework for running knowledge discovery application on cloud-based systems. Actually, the presentation is mainly divided in two parts. So in the first part, I will try to discuss the strategy. So one approach for the implementation of service-oriented distributed knowledge discovery task and application on, today we must say cloud because we are in a cloud-oriented conference, but I think that we can speak about large-scale distributed system or large-scale high-performance computing system. So we understand what we mean. So the idea is to try to outline an approach for the implementation of large-scale service-oriented knowledge discovery tasks as services on this kind of platform, and investigate how this kind of knowledge discovery or data mining services can be used to implement distributed data analysis application according to the service-oriented architecture model. So in the first part, I present the approach, and in the second part of the talk, I will give you some references to real projects we are running, where we develop some software according to this approach that show the feasibility of the approach and the the way in which these services can be used for real implementation of distributed knowledge discovery application. So, you know, we have to deal with complex problems, with bigger and bigger problems today, and most of them come from the, okay, obviously it's life, but the main issue here is that we have to deal with very huge data sources. So data sources today are larger and larger, and often they are distributed. Okay. So starting from this scenario, we have to deal with this huge amount of data, and we have to use this data. Okay. And obviously, we have a main problem. We have one problem, which is storing data. Okay. And it's a problem, obviously. But from my point of view, the main problem is not storing data. The main problem is to analyze data, to mine data, to process data, trying to understand it. So, you know, obviously, one problem could be or is having no data, having no information. But the other side of the coin is that having so much data that you cannot understand nothing. You cannot manage them by regular tools, or they cannot be read by humans. So having too much data is more or less like not having data. Okay. Now, just to mention some estimate, I am not sure how accurate is this estimate, but it's an estimate, okay? It seems that oh, sorry, it's not 2006, but it's 2009. Oh, the 9 changed its position. So it's in 2009, it seems that we produced 750 billion of gigabytes. And the problem is that in 2010, we are going to produce 1 zettabyte of data, which is an impressive amount of that. And just to show you I'm not sure if this is a point or no. Okay. This is the forecast produced by IDC, and you say, we have a problem with the available storage and the information created. So this, it seems, is the trend. So it's a very impressive trend. And so, starting from this scenario, we must be able to face this challenge. So to handle this very large amount of information and the associated complexity, which is related to the processing of this large amount of data. So the idea here is to use, as I said before, large-scale distributed system like HPC, cloud system, grid systems, peer-to-peer systems to provide efficient computation support for this kind of application and for analyzing this data, for discovering the interesting part of this data. We had some talk today and yesterday on this topic. Very, very interesting talks. So that seems are in accordance with this approach, and I'm happy of that, even if has been done by well-known and very expert people. So the idea here is to try to use this bunch of technology to support the implementation of integrated framework for doing analysis of data through services interface. Okay, so the basic idea is to try to identify single step of this big and complex process and implement each step. I will show you in more detail later as a single service, and then composing services in a sort of ecosystem of services that may run on this kind of large-scale infrastructures. Okay. Having at the hand a sort of data analytics clouds. You know, we have a big data center, and data center are used to store data, but not only to store data, to process them, to query them. And typically, the interface of data center is a service-oriented interface. So in this case, the idea is to add data analysis or data analytics services for handling with this large amount of data. And obviously, in this kind of infrastructures, we have security facility, resource information services, so to identify the resources we have in terms of data, in terms of software, in terms of hardware, and so on, communication mechanisms, scheduling, fault detection, and so on. That all this is a sort of basic infrastructure that could be effectively used for implementing data analytics clouds. Now, okay, when we speak about data analysis, we have to deal with data mining algorithms, so with the distributed and parallel implementation of data mining algorithm. That means adopting data parallel approach or task parallelism approach, managing data dependencies, having the possibility to define workflows or dynamic test graphs that obviously are based on data dependencies themselves, deal with dynamic data access, and all these aspects are part of the task, so the problem of implementing parallel data mining and or distributed data mining approach. You know, there are, so actually we may say that parallel data mining algorithm could be part of distributed data mining applications. So especially in a cloud, I may have complex data analytics application that run parallel data mining algorithm in some part of clouds, in some virtual machine, and these are part of a larger scenario, a larger application, which is distributed, for example, in a larger cloud or in some intercloud. Okay, and obviously we need to program this data mining operation tasks and patterns. So this is one key point for me, because my idea is to implement this data mining operation as a service, okay? That could be integrated among them. Obviously, you know, we may address the problem at different levels, and these different levels are not alternative among them. Okay, so obviously we need to use traditional approach, or libraries, languages, concurrent languages, and so on, as we know. But obviously this could be an alternative of this different approach based on components part, or could be part of the solution. Could be a way to integrate both approach. And on top of that, we should think about web services, grid services, so cloud services, workflow, mashup, and so on. Okay, if we go up, we increase the grain size of application, the grain size of tasks, and going down, we increase the number of processes. So the number of, the degree of concurrence we have. The grain of tasks decrease and the number of tasks increase. Okay. So to do this, we suggest to exploit the service-oriented architecture to define services, basic services for supporting distributed data mining application. In larger scale, as I mentioned before, larger scale distributed systems. For example, in private cloud, but in private clouds, but also in larger clouds like interclouds. Okay, so the idea is having services for data selection, for data transport, for data analysis, for model, knowledge model representation, and also for visualization. More in detail, the idea is this one. So, the idea is, okay, if you need to run a data mining application, okay, or knowledge discovery application, you need to identify the steps of your task, okay, of your application. Some of them obviously start from data, okay. You have to identify the data source on which run the analysis, and then, for example, preprocessing data, filtering data, and so on. So you need to prepare data for the mining, okay. So in general, in a KDD process, this is the first part of the process, and we think that each of these operations, so each of this single KDD step can be implemented as a service, okay? And you have services, for example, for preprocessing data, for filtering data, for transforming data, having them in the correct format for the analysis, okay? Going ahead, each single data mining task can be implemented as a service. For example, we may have classification algorithms, or clustering algorithm, or a priori algorithm, so association rule discovery, and so on. Each one of these can be implemented as a service, okay? You may have the code of this algorithm in Java, in C#, or whatever, but you may offer them as a single service, okay? So in each layer, we have a collection of algorithms that are offered as services. Then we can, in a distributed setting, compose single data mining tasks or single KDD steps to implement the distributed data mining patterns. Okay, so I want to run, for example, a parallel classification or a meta-learning application or a collective learning application that run on a large amount of, a large number of machines. Okay, I can take single services for analysis on a single machine and compose a distributed data mining pattern, a distributed data mining application. What is important is that also this one could be a single service, which is composed of a set of services that come from this layer. On top of that, we can go to have a complete data mining application or a complete KDD process as implemented as a single service and implemented as a collection of previous tasks and patterns. And typically this could be done in a sort of multi-step workflow, okay? Where each node of the workflow can be a single service or a multi-services in terms, so it can be composed of several elementary, or how to say, small grain services, okay? So we have a way to compose data mining application in which we reuse all the services in the lower level for implementing application in the top layer, okay? Okay, so at the end, we have a sort of open service framework for cloud-based data mining. So in this way, having single services and having a way to compose the services in an application, we allow developers to program distributed data analytics process of application as a composition of single or aggregated services available over a cloud. Okay? So these services obviously should exploit other basic cloud services, for example, for data transfer, replica management, data integration, and querying, that perhaps are already available in many clouds. Okay? And all this is a sort of ecosystem, service-oriented ecosystem for data mining. Okay, so at the end, this kind of approach may result in service-based distributed data mining application for communities. We discussed it before, the community of chemistry people or other scientific community that need to have a way to run data analysis application, or for virtual organization, so community of different physical organization. And we may have also distributed data analysis services on demand, because people may access the cloud and ask to analyze some data, okay, on demand. So at the end, we have a sort of knowledge discovery ecosystem. Okay, so I hope I have 10 or 5 to 10 minutes to, okay, just to show some examples of this kind of approach, because I try to outline the general approach, so the general way for implementing this kind of approach, and then I will show you some examples. Just to finish this first part, obviously we may wonder if data mining services are or are not programming abstractions. So in terms of, how to say, programming language approach, so what is this? Having, in a traditional way, this is not apparently a sort of programming abstraction proposal. But I think that we should consider it data mining services as programming abstraction, because if each single data mining algorithm, each single data mining application could be used as a small element of a more complex application, we should have mechanisms to compose them, so to program them to run more and more complex applications. So we have basic services as a simple operation, okay? And using service programming languages for composing them, like workflow-based application or workflow-based paradigm, we can compose the basic services for programming data analytics application. And obviously, we have complex services and their complex composition towards the implementation of distributed programming patterns for data analytics services. Okay, so just to show you some examples of the approach I presented here, I give you a very quick overview of 4 systems. I have no time to go in details, but we have a lot of material in case you are interested in all of these systems. And some of them are open source, are available on the web. Okay, Weka for WS is one approach of implementing the Weka toolkit, which is a well-known open source for data mining. The only limit of Weka is the that is running on a single machine. So it's a sequential application. What we did is provide an implementation based on web services, so we may run it on a large scale, so typically on the web, so on large scale infrastructure. The knowledge grid is another data mining framework, software framework for the implementation of the approach I proposed. And then we did some experiments in providing mobile data mining services. And this is very interesting because this is a way to couple mobile devices with cloud. So you may use the cloud running also, or requesting the running of complex application from mobile device. Okay? And then the last one is mining at home, which is an approach based on a peer-to-peer, architecture. Okay, just to show you some detail. So this is just the interface of the Weka for WS knowledge flow, in which you have a way to compose very complex workflow of data analysis, so an entire knowledge discovery process that typically starts from a data set that could be divided or partitioned in several data sets. And all this can be run in parallel on a cloud or on a web server, in which so each node can be run on a different machine. Okay, so the interface allows the user to program the application at a very high level, and then the system will run the application in parallel and move data where data is needed and move result back to the user when the results are available. Okay, so in this way we program a data mining workflow and run this workflow in parallel on a large scale distributed infrastructure. The same approach has been used in the service-oriented knowledge grid. So the idea is, as I mentioned before, we have a set of services. We have a way to compose the services and to run them on a distributed infrastructure. So what are the services here? The services are data access services, data mining algorithm offered as a service, distributed data mining patterns offered as a services, and so on. So you have a catalog of all the software and data you have available to compose your application. Then you look at the catalog of all the resources, so all the services available, and compose your workflow. Okay? So the workflow composition is very abstract. I will show you a slide of the interface. And then the system cares of running this in parallel on a distributed infrastructure. So the user doesn't worry of this transformation, of this passage, okay? And in this way, the user focuses on the services available on his application, not on the distributed details, on the architectural detail of the distributed infrastructure, okay? Yeah, the idea is this. This is just a UML, extended UML approach in which you compose your workflow and then annotate each node with some information about the algorithm or the tools, etc. But perhaps it's better to show this interface, okay? Because you compose your application as a workflow. For example, in this case, we take a data set, we split, because we have a splitter, we split the data on different partitions, and we run them on 4 machines, for example, okay? And then we collect the result and produce the model, okay? So the user have this kind of interface, okay? So this interface corresponds to this and this layer. Then when the application is composed and all the tags are green, so it means everything is available, you may say run, and this is run on a distributed platform. Okay. Okay, I'm going to conclude the talk just showing what we did with the implementation of a service-oriented mobile data mining framework. In this case, we have the cloud, we have a set of machines, and we have the client that are mobile. Okay, so here the idea is that we have data providers that typically are on the cloud and mining services, and mobile clients that are outside. Okay, so in this case, the idea is that you can have access to the resources, select the data set you need to analyze, select the algorithm from your mobile phone, and then say run. The application is run on the distributed infrastructure, and the result are sent back at the end. All this is done through a service-oriented infrastructure, to a service-oriented interface, because here is just a client for service invocation. Okay, so it's very simple. Okay, so what happens is that, okay, you can choose some parameters and then you see the result. Obviously here we have some problem with the representation of result because the screen is very small, but we provide an interface that allows the user to select which part of the result you want to visualize at which time. Okay, the last one is try to explode this approach in a sort of very large scale infrastructure using the public resource computing paradigm. So in this way, the idea is that to emulate the approach of SETI at home or similar and having mining at home. So in this case, obviously, the idea is that, for example, for community of scientists that share data that are public, typically, if you think about biology data or chemistry. Okay, I'm going to finish. And they may cooperate, sharing data, sharing machines, and obviously running application on this machine. So this is a sort of highly decentralized data analysis application that could be programming as a large collection of tasks and services. Okay, this is just a snapshot. Okay, so yeah, obviously we evaluate the impact. So I mean the overhead of services, and typically the overhead is not so much. So it's a very small percentage. So having the application, offering the application through a service-oriented interface does not complicate, does not add a very large overhead. So this means that it's feasible. Okay, we did some speed-up evaluation. Okay, this is just the last slide, just to conclude. So the idea is that, okay, as I think all we agreed, the high-performance computing infrastructure may allow us to attack new problems, but they require to solve more challenging problems, and perhaps new programming models and the new programming environments are required. So, and this programming framework should be devoted to manage data and to analyze data, because data is becoming a very big player. So programming data analysis application services is a must. Okay, in a long-term vision, this approach may bring to a sort of pervasive collection of data analysis services and application that must be accessed and used as public utilities. And I think that this approach is in accordance with the approach that the cloud community is pursuing, so it's running in this moment. Obviously, we must be ready to manage this kind of very complex scenario. Okay, thank you very much.
Unfortunately, we only have time for one question, but
okay, we have time to discuss later. Yeah.
So if there's any questions, we can start with one question. Kick things off. We'll be great.
I'd just like to give a comment.
Yeah.
In the most humble sense, I think you should reconsider your use of the red color during the slides, because sometimes they attract the attention for what's not the essential part.
Okay.
It's not cultural political.
Thank you.
No, I just wondered whether you have, it would be possible, maybe you both can answer the question.
You may start.
No, of using workflows to deploy the combination, a composition of the mining.
I can only say that's a great idea that I saw in your talk. That was one of the nice ideas I saw in your talk. Is abstracting away service request into how to act.
Exactly.
Which I think is great. I love the hierarchical approach you're taking.
Yeah. Yeah, because if I can add something, because users of this kind of system often are not computer scientists. So people, scientists or business, I don't know, technical support to businessmen should focus on the application, not on the architectural details. And perhaps workflow or service-oriented approach could help.
I'll just add one thing, just based on my experience with workflows, is that often we talk to financial analysts about their pipelines. They're doing different computations, but if you look at the core level, they're using the same functions with different parameters in different ways. So it scales very nicely. If you implement those 20 analysis algorithms, you could support 100 pipelines at the workflow level by combining them. So it's very nice. Let's go have a
Okay, thank you very much. Thanks.